Okay, hello. Hello, everybody. Again, now in the session with Viola Priesemann. So it's my great pleasure to very briefly introduce her. So she's a professor at the University of Göttingen, and she's also at the Max Planck for complex systems. And she is going to talk about some more about actually balance. So I'm very much looking forward to your talk. So without any further ado, please.
Yeah, thank you very much for the kind invitation and also for an opportunity to present my talk here. And I think it's in terms of topic fitting very well. I'm presenting today dendritic balance enables local representation learning in spiking neural networks. So we concentrate on one work that I did in the past 1 or 2 years together with Fabian Mikulasch and Lukas Rudels, two very talented and active PhD students in my group. You can find it here on arXiv. So local balance. If you look into learning in living neural networks, there are a number of challenges. Neural systems learn complex statistical relationships in their environment despite facing severe constraints. The learning, at least in part, uses locally available information only and not the global one compared to artificial networks, but it's much easier to bring any information to any point. I think that's an old point by now. We have neural signaling that is delayed from one neuron to the other. That's something I would like to stress here because it becomes relevant later. And complex correlations in the inputs need to be disentangled. So if apples and bananas tend to occur very often, you don't want to have an apple-banana neuron, but you want the apple neuron and the banana neuron individually, bluntly saying. So the outline, or let's say the take-home message here of the talk is the following. We look into learning with somatic balance. We will abbreviate it with SV. And we'll show you, as known in the field, that it fails when neural activity is correlated because the hidden features of the inputs are then correlated. That leads to the correlated neural activity. And because the neural transmission delays, they tend to fail to regulate the Hebbian learning that makes the connections between neurons stronger. What we want to propose is to put the learning from the soma into the dendritic compartment. That's a short, the one-sentence summary, putting the learning from the soma to the dendritic compartment, which means also putting the balance to the dendritic compartment, and use, as before, the idea that the local balance represents the error signal, and that this error signal then is used locally for the update of the weight. This is all I want you to take home, and now we go into the details. So the solution is that dendritic balance enables local error computation in each dendritic compartment, and this implements the exact gradient, whereas the somatic balance is an approximation. So learning an efficient spiking representation of neural inputs, one typically goes ahead with that by minimizing some decoder loss between the stimulus and the estimated version of the stimulus. And in spiking neural networks, we want to keep the average firing rate fixed to some reasonable value. A implementation, you might know the figure here from Deneuve and Machens, is to have, for example, feed-forward excitatory neurons and some lateral local inhibition, and that then leads to the required properties, which is precise temporal coordination of the spikes. What does this classic paper show? It shows that a stimulus, X here, if it increases, can be represented by a group of neurons, and the lateral inhibition makes sure that they don't spike all at the same time, but they coordinate such that then the population rate of that group of neurons follows very well that teacher signal. So the second part that we also know and have a lot of aspects and knowledge about is how to learn the regularities of high-dimensional inputs. Since the 90s, literature is really out on that, but the challenge that we are often meeting is that of implementing and accounting for delays there. So if we now dive a bit more into here, this schematic of a neuron at that local lateral inhibition, how does it look like? So this should be a neuron now. It should be red, obviously. We have some lateral inhibition, and at the soma, then the lateral inhibition that comes in together with the feed-forward input in red, they should cancel each other. That's a goal that one has for optimal representation. The feed-forward we indicate with the F for feed-forward. These are the weights for feed-forward, the lateral inhibition by W throughout. And here we do have the tight somatic excitatory inhibitory balance because that then encodes at least approximately the error as long as because it basically has an average of all the neurons that are representing the activity and the encoding of that entire stimulus. So how does the learning then work? Here on the right-hand side, you see the development of the decoder loss over time for this extremely simple MNEST part. If we start with completely naive network, which means random synapses, then the feed-forward weights are randomly drawn, and we have some starting value of our decoder loss. The representation, these are basically the synaptic these are the feed-forward weights, and these are then the optimal readouts. You see that the representations are not well disentangled. There's these mixtures of 2s and 0s. For this example, we only represented 0s and 2s for the heck of simple representation, but it can obviously generalize to more patterns than that. Then at some point, we put on the feed-forward input with the Hebbian type of a learning that leads to a reduction of the decoder loss. The representation becomes better, but it's still not not perfectly disentangled. If one in addition then learns the lateral, this is for the recurrent learning. If one in addition then learns the feed-forward weights here optimally in a Hebbian-like manner, which means the neurons really become selective for specific type of features, then both the feed-forward and also the decoder show a fairly good representation of our 0s, 1s, and 2s. This is the standard way of how many of these networks are learning. So where is the challenge? The challenge is, as I said, in the correlated input features, apples and bananas occurring too often together, and in the transmission delays. And therefore, we extended that picture of the somatic balance to the dendritic balance. And in principle, the entire derivation, I decided not to go into the details of all the derivations, but they are done exactly in the same manner as you would do it here for the somatic balance. You minimize your loss, you project it to the compartment, but instead of projecting it to the soma, by projecting it to a local compartment here, you can bring together the weights, and you have way more degrees of freedom to then represent at every single dendrite the error that you have from the feed-forward weight in relation to the representations that all the other lateral neurons basically have. And the lateral neurons then via some inhibition represent what they are encoding. If we have such a local representation, then this is an exact gradient for f that we can, for the feed-forward weights, that we can represent, while the somatic balance proper has and is by definition an approximation. That approximation works very well, as I show you in the following example, but it fails under the more complicated settings. So what does it mean for the learning rules that come out? The learning rules that one derives for the somatic balance, here on the left-hand side is the somatic balance, that learning are basically pairwise Hebbian-like plasticity with increasing of the weight if the firing is at the same time, which basically says a neuron then selects a certain feature it represents. The absolute offset here depends on the neuron's proper strength. In addition, we have some fast adaptation. What do we find for the dendritic balance in terms of its local learning rules? We do find that the learning rule of that feed-forward weight depends on the local error. The local error either makes the learning rule STDP-like with positive terms on the pre to post-synaptic spiking, or it makes it anti-STDP-like, where if the error becomes negative, which basically means that other neurons are already encoding your specific feature, then if that error is negative, this rule is inverted effectively. And thereby, we make sure that all the different features you have in your input are represented in a distributed manner across the neurons. I would like to demonstrate it here. So any natural images have some correlated hidden features. Also, the scenes then have correlations. I'm always talking about the apples and bananas that might co-occur at least in your supermarket. But that's an absolutely general feature. But we because we have a small network and also the calculation of the learning rule is a bit complicated, we decided to go for a fairly simple task, and we also wanted to have a full control over the correlation. So what do? We take a bar task with 5 times 5 bars, and we always show 2 bars, an apple bar and a banana bar, whatever you want to think about it, and these can be completely independent. So this correlation or probability of co-occurrence is 0. The other set that we then have is that we have a certain probability. The second bar is just the flipped one, the diagonally flipped one, and with probability 1 minus p, it is just a random other one. So in this set of stimuli, there's only these pairs of bars occurring. That also makes obviously the decoder loss lower. But with then probability close to 1 but 0.95, there is in principle the 2 bars also occurring independently, and a good encoding would be able to disentangle the 2. So this is then the performance for using somatic balance. It's fine as long as there's little correlation, but then the more correlations there are, the better, the worse it becomes. Then if we have instead a dendritic balance where the error is computed locally at every single compartment, then the error becomes the error becomes better, the decoder loss becomes better. This is because the entropy of the stimulus goes down. So what we see here as a decrease is the entropy of the overall stimulus being reduced. So, and not only the entropy being reduced, but then also the different neurons learning disentangled representation, and not, as we can see here, neurons that are representing always these joint pairs of the bars instead of mainly the independent bars. This also works if one puts natural images in. We pre-process the natural images with the retina-like feature, and then one can see that no matter how many neurons we have in the systems, between 250 neurons, so it's fewer neurons, the task becomes more difficult, decoder loss goes up, that's absolutely clear. But what one does clearly see is that no matter what is the number of neurons, the dendritic balance performs better. So that was about disentangling correlated input. The second challenge is the transmission delay. Why is it? Imagine one neuron codes for the banana, the other one codes for the apple. They should inhibit each other, but if they're both basically coding at the same time, inhibition is too late and therefore does not reduce the feed-forward weights, the Hebbian-like feed-forward weights. And this is something we do see here, that if we increase the delay in our simulation, then we find this breakdown of decoder loss for the somatic balance implementation. And this image here illustrates what's happening in the neural network. So here in the somatic balance, one sees both aspects. One sees that the representations don't become as crisp and clear as they become in the dendritic balance, and you also see how the neurons basically are spiking in a highly synchronized manner instead of an asynchronized manner. So that with the synchronized manner, we have this burstiness of excitation inhibition flipping back and forth. Do we find evidence for dendritic balance in vivo? And we do think we have some. So there's this older but classic study from 2004. They measured excitatory and inhibitory currents at these spines, and they did find that there was a fairly good balance if the spines were at the same dendrite compared to a balance of spines at different dendritic compartments. The other evidence that we have is that the balance indeed might influence plasticity. Here are some LTD protocols, either with or without, so without or with GABA, and only with GABA, which would decrease the local dendritic, or would decrease the local membrane potential. Only with that we find the decrease. So that is at least some indication that the local membrane potential might not only be well balanced, but also play a role and shape the neural learning rules. So in summary, the dendritic balance enables local representation learning. Dendritic balance provides the local error for representation. It enables local learning of feed-forward and lateral connection, and this links the computational theory with a concrete biophysical mechanism. So putting the error and the learning from the soma into the dendrite, I think, makes overall neurons way more powerful potentially than they have been before. And if such a implementation is possible, then often, let's say, neural networks will probably have managed to learn or find that in via evolution. With this, I really want to thank my group, especially Fabian and Lucas, and I welcome your questions.
Thank you very much, Viola. There are some questions. So the first one was actually in the chat, but since it came out first, I'll just read that. So this was Tim who was asking, how is actually the local error defined?
And the second question, with any drawbacks having dendritic balance. So one drawback I should have been more open about that, but it often comes, is that for the dendritic balance, as you can see, we basically bring in the representation of all the other neurons to some local compartment. So in principle, at least in theory, if you don't want to make any approximation, this is an all-to-all connection to that local compartment. And you can see that the number of connections explode. What we did numerically, but it's not yet in the paper, is to just prune away 95-ish% of these connections, and then the network still works very, very well. So in theory, it's necessary. In reality, it's not necessarily needed. How is the local error defined? That local error is literally the lateral input. So it is the encoding that all the other neurons have chosen, projected via the lateral weight W to that local compartment. And the error then is the membrane potential, the difference between the feed-forward excitation and the lateral inhibition.
Good. So then there's another question, which is by Livius, who's asking, I guess the network is trained in a supervised scheme where labels are used at some point. I guess it's a reconstruction, actually, in a way. But if so, do you think we could use the same learning principles with a sort of winner-take-all network at the output layer to introduce competition and hence learn the representations without supervision?
Actually, this is unsupervised. I should have stressed that. This is unsupervised learning. Why is it unsupervised? Because you want to optimize the representation. How do you optimize representation? This basic principle there is that you want to basically balance the feed-forward input and the lateral inhibition. Lateral inhibition is how the other neurons are representing what's out there. And if I say that very sloppily, let's say to my students, I say, well, if another neuron already says I code for the banana, then it inhibits your apple neuron, and the apple neuron should shut up. And therefore, you have an emergent, unsupervised representation of the hidden features. These hidden features are the bananas and apples in your supermarket. And ideally, you don't represent them by pixels, but you represent them by their object categories. Apple, banana, and whatever you find there in your supermarket. And the important part is that it's well distributed. And now the second step is, yes, if you would only show one stimulus at a time, then it would be easy. Then your stimuli are perfectly decorrelated. But in your supermarket, the apples and the bananas are often coming together. So you want to be able to present both. So it is not a winner-take-all. It is the same idea as a winner-take-all-ish because you have the lateral inhibition, but only a very, very soft one in the sense of it's possible to represent as many of the hidden features at the same time. And they can even occur in very correlated manner. And that is the strength and the strong advancement here in the field, I think all of that field, is that we can disentangle them even if they occur together. I mean, they would, for other networks, then look like an apple banana, a joint object. And this, if it's sufficiently often, let's say more than at least 5%-ish of the time occurring independently, then we can, with these type of networks, disentangle them. I mean, there's not a hard bound, or we didn't properly look at the bound. This is just the estimate from the current data. So yes, it's unsupervised. I would like to stress that. I should have been more clear about it.
Yeah, he's very excited. So he commented just on this question. So unfortunately, we can't do two more questions. I'll just ask one. We have like basically 10 seconds. But Matteo Zuppanati asks, thank you for the interesting talk. Did I miss something, or does this model also require heterosynaptic plasticity?
In a way, it is not necessarily heterosynaptic plasticity. It depends on how you specifically define heterosynaptic plasticity. All it needs is you want to have the plasticity of the feed-forward dependent on the local membrane potential, The membrane potential probably is local. We know experimentally that the inhibitory currents tend to fall off within a few tens of micrometers or more, but there seems to be locality. So it's indirectly heterosynaptic in the sense of the other synaptic input playing in a role via the dendritic membrane potential that you measure at a given time.
Okay, great. Thanks. Thanks also for the short answers. So there was one more by Arash, which I'll post in the chat so it's not lost, and maybe we can get back to it later. Unfortunately, we have to move on now. Thank you very much for this very nice talk, Viola, and thanks for coming. And with that, we'll move to the next session. Great, thanks.
Thank you.